Hello, everyone. My name is Jerry An, and I'm a recently graduated Systems and Control Master student at TU Delft, and also was a visitor to the Intelligent Control Lab at CMU. And I will be presenting this work titled Flexible MPC-based conflict resolution using online adaptive ADMM on behalf of myself, Jerry An, and my two supervisors, Julia Giordano and Charlie Liu. First, we need to ask, why do we need conflict resolution? And why decentralized? Well, first, there's quite a lot of issues right now related to traffic congestion. For one, it costs a lot of money. For example, 160 billion in the US alone a year. Urban infrastructure is also not quite ready for connected and autonomous vehicles. And that is in urban environments. Outside of urban environments, for example, for rural roads, highways, parking lots, this is even worse. Centralized methods, well, they are prone to attacks and outages. You basically only need to take out one node to take out a large part of the network or the entire network. They also have poor scalability, mainly due to the essentially combinatorial problem of scheduling these vehicles. And also they require quite expensive infrastructure, which we are not equipped for. So for that reason, we want to reduce congestion by resolving conflicts efficiently for autonomous vehicles, and also use decentralized conflict resolution method instead of a centralized one. So what exactly do we want? Well, in words, essentially what we want is to solve conflicts between autonomous vehicles in a decentralized fashion with minimal delay. And in terms of maps, that looks like this. So it's a minimization problem with some constraints, so where we want to minimize our cost function, where x is essentially our trajectories, which we want to be feasible always, and also without collisions with other vehicles. So how do we accomplish this? Well, we use a combination of model predictive control and online adaptive alternating direction methods of multipliers. So first, let's have a quick summary of MPC for those who are not familiar with it. Essentially, it's a predictive control method where a cost function is minimized for a certain finite horizon. And this can be used to perform motion planning and control for autonomous vehicles. So the key aspects are that it's optimal for the finite horizon. However, optimization can be slow. They can enforce constraints, but those constraints can then again be not easily decentralized. So alternating direction method of multipliers is a way to incorporate this, as it is essentially a distributed convex optimization strategy and can speed up difficult optimization problems. So it's designed for problems where you have basically two functions that have separate costs, but are, however, linked for a couple of constraints. And that can then be solved iteratively and also parallelized. So online adaptive ADMM is essentially an extension to conventional ADMM, where we adjust our static penalty parameter rho into an adaptive vector. This is in combination with a adaptation function, phi, which essentially dictates how we are going to update our rho, and a similarity function mu, which can be equated to a forgetting factor. So this is a general framework which allows for improved real-time performance, where we have proven offline convergence, whereas online convergence has the same issue as MPC in general, where persistent feasibility is not easy to prove, but you can use, for example, reachability analysis. And a properly designed adaptation function essentially enables faster convergence and also more robust behavior. And a properly designed similarity function then allows the system to recover from time-dependent disturbances. So the strategy for our approach first involves formulating the problem into a separable MPC form. So essentially, we still have the same problem. However, by adding a slack variable z, or essentially a copy of x, we can now have separate feasibility constraints and separate collision avoidance constraints. However, by restricting these to be equal, we still have the original problem. But since ADMM is meant for addressing coupled constraints, as we mentioned before, this is now easier to apply ADMM to. So essentially what we do is we separate our problem into an X update, which does parallel cost minimization, which is still feasible and thereby can be executed by our vehicles, and a collision avoidance update, which essentially can be used as a reference for what trajectories are safe. So to do this in decentralized fashion, we basically have to communicate between steps. And essentially what you can see here on the bottom right is how that diagram of OA, ADMM, and MPC looks. So essentially we start with the X update, then we communicate this with other vehicles, and then every vehicle in parallel then computes their own Z updates, and then also in parallel they can do their own lambda update and their own rho update. This is then also communicated to all vehicles, and then each vehicle follows their own planned X trajectory. And this is then repeated. So let's take a closer look at our optimization steps. We have the parallel cost minimization step and the collision avoidance step. So essentially, the reason they are called this is because, well, our X update or parallel cost minimization step always results in a feasible control input. And our collision avoidance step always results in collision-free trajectories. So how do we combine that? Well, we use a Lagrange multiplier update and a penalty vector update. So what does the Lagrange multiplier update do? This is essentially the same one as conventional ADMM. However, we add a similarity function, which essentially acts like a forgetting factor. However, the penalty vector update is unique to OA ADMM, where we essentially use an adaptation function phi to adjust our rho in real time. So what does this function phi look like, or how do I design one? Well, this is the one that we use. And the intuition behind it is essentially that the smaller the distance between vehicle trajectories, the more we want to penalize collision avoidance costs. And then we also, for robustness, we bound it. So that's why you see this phi min and phi max, which are our upper and lower bounds. And what you can see here is essentially a function that increases the closer that planned trajectories are to each other. And we can then adjust the shape by adjusting A and also adjust our desired minimum distance by adjusting the min. But essentially, yeah, it's a barrier function. However, based on the physical planned trajectories rather than basing it on optimal convergence. So to compare our method with other decentralized protocols, we need to design a benchmark. And we do this in Carla, which is an open source vehicle simulator. So the two methods that we compare against are AMPIP and TVCR. These methods use a simple collision avoidance method where they allow vehicles to reserve time slots on a grid map using a heuristic method. AMPIP is quite simplistic in that approach. They don't use any optimization at all. Whereas TDCR uses some optimization, but only for velocity profile planning. So it's only optimization in one dimension, essentially. And the way we perform this benchmark is by simulating all scenarios which involves two vehicles arriving at an intersection at once. So you can see those scenarios depicted in the top right. And the metric that we use is the added delay. So what we do is we compute the delay for each protocol and then compare it with the estimated delay, which is essentially based on the conflicting part of two vehicles' trajectories. So the results show that OA ADMM has lower added delays than all the other protocols, has about a 60% reduction compared with AMPIP, and about 50% reduction compared with TVCR. And those are both with high fidelity grid maps, because if you only allow, for example, one cell for the grid map, for the entire intersection, you will get way, way larger delays. So competing methods are highly dependent on the prior knowledge of the environment, whereas our method only requires relative positions and relative trajectories, which you can do easily with the amount of onboard sensors that all of the autonomous vehicles are equipped with. Also, competing methods can only adjust their velocity along the path, whereas we can also adjust our path. So that can result in also reduced delay. For example, when two vehicles want to turn left at once, if your grid map doesn't allow it or the planned trajectories do not allow it, they might need to pass sequentially, whereas we can adjust these trajectories on the fly. So here we have a visual example of OA ADMM MPC. And something that might be nice to pay attention to is that vehicles will be actually adjusting not only their velocities, but also their paths. So to summarize, OA ADMM is a novel framework designed to enhance the application of ADMM or distributed optimization in general to real-time problems. By combining OA ADMM and MPC, we can achieve decentralized conflict resolution, which is more efficient than competing methods, requires less prior knowledge than competing methods, and also allows the user to easily design the trade-off between optimality and safety. As for future work, we can take a look at improving guarantees for online convergence of OA ADMM under certain conditions. We can also take a look at integrating other collision avoidance methods such as velocity obstacles or probabilistic models using the adaptation function. So this would be really nice when we want to apply this method to, for example, mixed traffic. Another important thing is to explore the optimal adaptation or similarity functions, as they are now still designed by using intuition, essentially. And another nice thing might be to use nonlinear MPC, as linear MPC has some prediction errors, which might result in worse performance for OA ADMM MPC. Thanks everyone for your attention, and I will now be answering some questions.